Okay, so I start again. So welcome everybody, and thanks for joining, also those remotely. So today it's a pleasure to introduce to Mireia Montes. She's a researcher from the Institute of the Canary Islands, ICE, where she did her PhD. And then she moved to Yale for her first postdoc, then to Australia. I don't know exactly where, but in Sydney. And then she went back to the US in Baltimore, and then back to the Canary Islands for another postdoc. And now she got this year a Ramon y Cajal Fellowship, and she's considering joining the Institute. So we thought it was a good idea to invite her so that she has the opportunity to introduce her research. So anyway, so you're good to go.
Thank you very much, Pablo. So yeah, as Paulo mentioned, my name is Mireia Montes. I'm still a postdoc at the Instituto de Astrofísica de Canarias. But as Paulo mentioned, like I finally saw the lights at the end of the tunnel, and it seems that like not being the eternal postdoc, it's beyond my it's at my reach. So today I'm gonna talk to you about the science that I'm doing, which is what we call basically the low surface brightness universe, which is basically things that are very faint. Particular, what I'm like more known for, let's say known for, is this topic is the intracluster light. So of course it doesn't work. So our knowledge of the universe is biased to the things that we can see. One of the surveys that is most well known for the things that have provided us, the knowledge it has provided us, is the Sloan Digital Sky Survey. So it's allowed us to study many things, but in particular, my field, the extragalactic universe, with enough numbers to understand what is going on. However, as I mentioned before, what we know is very biased towards things that we could see in Sloan, which is things that are bright. So the thing is that we already know that like there's things beyond of what we could see with Sloan. For example, this is an image of M83, and this is a photographic plate. Because just mention here that with CCDs it took a little bit long to get into to the depth that we could see with photographic plates. This is a very iconic image of M83 by David Malin, and you could see that, for example, this is the typical image of M83 that we see, and on the right, this is what actually waits for us if we go deeper and deeper. And this is what normally is known as the low surface brightness universe. So it's basically the universe beyond Sloan. And the thing is that the low surface brightness universe, as we know it encompasses lots of things. For example, we can study the zodiacal light, which tells us about the evolution of our solar system. We can also study what is called the galactic cirri, which is the dust of our own galaxy. So we can study the properties of the interstellar dust. And also we can study low surface brightness structures around stars, around dying stars. So it can tell us about mass loss processes, about stellar evolution, etc. But where this field has shown is basically in the extragalactic realm. So, so when we go deeper and deeper, we start seeing the dwarf galaxies, like low mass galaxies, and this is a very interesting spot because it's where we start seeing the difference between the predicted number of galaxies and the observed number of galaxies. So the thing is that, because in surveys like Sloan, we are missing a lot of these low mass galaxies. So around 50% of low mass galaxies are lost, down to 10 to the 8, and even 85% if we are going a little bit lower in mass. So the thing is that we don't know if that's, like this disagreement between the predicted and the observed are due to, like that we don't understand galaxy formation in these realms, in these low mass galaxy realms, or because we are basically missing them. And that's why, like going deeper and deeper can tell us a lot about our universe and about, like basically the nature of dark matter. Also, we have, as we go like into, like higher and higher masses, we have what is normally known as the stellar halos. So this is a simulation of, this is a galaxy. And as we go deeper and deeper, we start seeing all this wealth of structure around this galaxy. And this is what we call the stellar halos. So we can see, like the streams, this more like diffuse light. And that also tells us about the number of low mass galaxies and about the properties of galaxy evolution and the properties of the dark matter halo of these higher mass galaxies. And in observations, it took a while to reach what simulations were telling us. But now we are seeing more and more all this structure around these brighter galaxies. And if we are going into, like higher mass systems is where we end up, with this, the intracluster light, in galaxy clusters. So I don't know, like, I guess that you've seen that I really like a little bit, like a snaps of history. And I think that is very worth mentioning that the systems of this diffuse light in galaxy clusters was first proposed by Zwicky in 1937. So he didn't see that, but he actually proposed in one of his papers of the Coma cluster that there should be some material in the cluster that is basically so these stars and matter from disrupted nebulae that we were not calling at that time galaxies, they were nebulae, in this space between the galaxies of the cluster. And he actually observed that in 1951 again in Coma. So what is that? So in simulations, we see that this very diffuse light corresponds to this extended component that you can see here in the left in blue. That actually corresponds to stars that have a higher velocity dispersion than the stars that correspond to the galaxies of the cluster, to the stars of the cluster. When we go to the observations, we see that as we build the profile from the BCG, the brightest cluster galaxy, the most massive galaxy of the cluster, to the outer parts, we see that this diffuse light is an excess of light in the outer parts of this very bright galaxy. Also, we see that the ellipticity increases with radius, and also sometimes you see a change on the position angle of these ellipses. So that is telling us, all these three things together, this is telling us that this is a separate stellar component. And actually, when you go to, like to the closest clusters where you actually can basically or do spectroscopy or have like some sort of tracer like globular clusters or planetary nebulae, you see that the velocity dispersion of these stars increases with radius until it reaches the velocity dispersion of the galaxies of the cluster. So basically, we understand this intracluster light, this diffuse light, as stars that are not bound to any particular galaxy, but float around following the potential of the cluster, which, as you'll see later, it's a very nice definition, but it's really hard to actually impose. So this is, I think, that probably the most iconic image of the intracluster light. This is the Virgo cluster. And you see, like the very diffuse light that basically there are no empty spaces between the galaxies of the cluster because this light extends kiloparsecs. But you also see that there are stellar streams here and here, and somewhere over there. That basically this is telling us about the origin of this light. So, and I think that the best way for you to see where this light comes from is a move. So basically, like you have like your galaxies that are interacting in the cluster, and the stars of these galaxies they get ripped from their galaxies and end up populating this intracluster space. So, well, as you could have guessed, because it's the loss of brightness universe, this light is really, probably in the middle, is really faint and is kind of hard to study. Sorry, I had to mention here that because this light comes from the interaction between galaxies in the cluster, so you have all these interactions that like produce this intracluster light. You have a record of what happened in the cluster. So by studying the properties of this light, you have like an idea of what happened to the cluster before. But also, if you are not for some reason you are not interested in galaxy clusters, but you say like, I really like very massive galaxies and I really want to understand how they evolve. So the most massive galaxies in the universe are the brightest cluster galaxy, the BCGs. And actually, you cannot understand how they become what they become if you don't take into account that there's intracluster light there. So in this plot, this is the evolution, the growth rate of these massive galaxies, of these BCGs. And you have here the points are observations. And as you can see, the observations are all over the place. But the thing is that in simulations, actually, the simulations predict a much higher growth rate than what actually we observe. But if you do some simulations and you have that some of the mass that is, instead of going into this BCG goes into this intracluster light medium, you have a much better agreement between the simulations and the observations. So, well, the intracluster light is really faint. And the problem is that with things that are faint is that we don't have observations. We rarely have observations that are deep enough that we can actually see this light. So the theme here is that we basically know very little about the intracluster light, but we know some things, and I'm gonna show you what we know and what we don't know, which is a lot, but anyway. And of course, like shameless advertising here, as you should always do, is if you want to know more detail about the intracluster light, I have 2 reviews that you can look at. So the main problem is, as I've said a little bit before, is that we don't know how to define the intracluster, which is really funny because you are studying something that you cannot define. So as I said before, so the intracluster light is this extended component that so on the left we have simulations, and on the right we have observations. So we know that is this extended component that actually it's a component, it's what we call a hot component. So the velocity dispersion that those stars in the intracluster light have is way larger than what we have in the galaxy or even in the halo of the galaxy. So this is a really nice, like stars that don't belong to any particular galaxy, but float around following the potential of the cluster. It's really nice definition, but the fact is that we normally have only images. You go beyond, I don't know, Virgo, Fornax, it's all tip images. So the problem is that observationally this is not possible because we don't have any kinematic information. So we only have light. So what observers have done is trying to define somewhere randomly this intracluster light. So and I'm gonna go through some of the definitions, the most common definitions of this ICL. The most famous and the easiest to do is what we call the surface brightness cut. So basically, it's any light that is below a certain, probably randomly defined threshold. All the light fainter than that is what we call intracluster light. So, for example, here we have Abel 85, one cluster of galaxies, and you see that when we impose the surface brightness cut, we have all this light left, and we have all the other light, that is associated to other galaxies in the cluster. The problem with that is that we have the light that, as you can see here in the plot, that is in projection to the BCG that we are basically losing here. So another way of defining the intracluster light is what we call composite model. So you use two or more than two, even three models to characterize the galaxy, the BCG, and the intracluster light. Problem with that, as you can see here in the same image of Abel 85, is that you characterize the galaxy, you can characterize the intracluster light, but you lose all these asymmetries or all the light that is associated with subgroups or other asymmetries that you have there. So like now, more and more, there are like this kind of hybrid way, which I call it wavelet-like methods. That's basically, it's kind of a scale filtering. So you are only getting like the largest scale, which is what you would define as intracluster light. And then in this case is you will end up having like all these asymmetries and all these things that you cannot capture with a normal composite model decomposition. Problem with that is that we have very few clusters because this is very computationally intensive. So like the surface brightness cut is like the easiest way, and this it's a little bit more involved, and we will see in the upcoming, with the upcoming surveys, how this is gonna perform. Anyway, so let's go to the things that we more or less know. So in simulations, all the simulations agree with that there's a correlation of the ICL with time, with redshift. So more or less from redshift 2, redshift 1, we see that there's an increase of this light. You can see here, so like a kind of rapid increase of this light. But of course, this is where we come with the observations. So in the observations, and that depends a lot on the definition of the intracluster light, we can see as well in the gray points are the surface brightness cut, and you can see that there's a rapid increase below redshift 0.5. But if you see to the black points, which is the composite model, you see that this increase is not as strong with redshift. You can see here like a little cartoon of this. So problem is that we want to study this evolution with time because it tells us about a lot of the processes that are generating this light. So, for example, if like instead of a really sharp increase, we see that the thing is more constant. It means that most of the light was created, at higher redshift and not enough. So basically, we cannot say a lot about this because we don't know how to define the intracluster light. So that is a really big unknown that we have. Well, we can also study how this intracluster light correlates with the mass of the system where it is. And here the simulations do not agree. There are some simulations that predict basically no correlation. Some predict an increase of the fraction of this light with mass. And there are some of them that actually predict the contrary, like a decrease of this fraction of light in this component with mass. And when you look at the observations, well, the problem again is that we have very few points, and some of them, as you can see here, that have like really large errors. So it seems that there's no correlation with mass, but well, we have to see because the errors are really, really big. There's have to say that there's also a new study from Rosella Ragusa that actually was that has something. It's a study that is more homogeneous because it was using the same definition, the same telescope, the observations that are of the same depth, and actually found the same thing, that there's no correlation with mass. So also, if we study the stellar properties of this intracluster light, we see where those stars come from, the host of the previous host of these stars. And here the simulations show that there are several ways of creating this intracluster light. So for example, you can have like a total disruption of dwarf galaxies. You can have the tidal stripping of more massive galaxies around the Milky Way-ish. You can have the what is called the violent relaxation after major mergers. So basically, like you have a major merger and the stars go out and populate this intracluster light space. You can also have what is called pre-processing. So you have a group or a cluster that is merging to your cluster, and in this cluster there will be intracluster or intragroup light that will end up being intracluster light in your cluster. And also there are some simulations that predict that there's some star formation happening in this intracluster light space. The good thing is that we can actually those different mechanisms actually have different ways of showing up in the stellar populations, in the colors or in the age and metallicity profiles. So when you look at the intracluster light and if you're lucky to have a color, you see those gradients in color that are also seen as gradients in metallicity, and in some cases there are gradients in age. So basically, these gradient metallicity and the metallicity that you can see in this intracluster light space are consistent with having, like being the tidal, that most of these intracluster light come from the tidal stripping of Milky Way-like galaxies. But of course, this is not as, of course, like this is the real life. And of course, things are not as easy. There are, in some cases, you see, like a flat color gradient. And of course, we are bear in mind that this is integrated light. So this is broadband photometry. What we see is basically the stars that contribute the most to this light. Of course, if we go to the Virgo cluster, we start seeing that there's a contribution of well, there's a greater contribution of all types of galaxies and all types of stars. And this is an inset of more shameless advertising here. This is and I'm sure that you are very, very familiar with this. This is the cluster SMAC 0723, which are the first observations of the released observations of the JWST. So this cluster is at redshift 0.4. It's actually, maybe it's a little, they call it JWST deep fields. Maybe it's a little bit too old already, but the cluster was observed 2 hours with JWST. So right away when the images were published, and we were my colleague Ignacio Trujillo and I, we were in a conference in Naples, like in the mountains of Naples, and with a very shitty Wi-Fi. What we were struggling to download the data, because of course there was a cluster of galaxies and we needed to see that. So we downloaded the images, but we found that the thing that you see here in the left is that, well, JWST is still a young observatory, and there are still things that are not quite figured out. So as you can see in the original images, you see a gradient in the images, which, if you want to study something that is very faint, it kills you. You really, because if you derive like a color profile or like a surface brightness profile or anything, you basically that this is messing up with your observations, with your results. So what we did is a kind of like a quick fix, and we ended up a quick fix, well, a quick data reduction to end up with the image that you see here in the right. And because now we have data that are good enough to study the intracluster light, what we did is basically study the intracluster light. So on here, as you can see, the cluster is quite elongated towards the east-west direction, and you see there's a lot of substructure in this cluster. You see here like a kind of a loop here and some tidal streams, and probably you see here better in this inset, like some sort of elongation of this BCG. So as we have colors, we can study, like the color profiles of this. So we see that at around 100, 150 kiloparsecs, the profiles are really, really flat. And then you start seeing like a decrease with, some bumps or, some structure here. So for the inner parts, we see these plumes here, which is basically this elongation that we see in this east-west direction. And we see that the stellar populations are quite homogeneous, which is telling us, because if you go from the center of the galaxy to the west or to the east, and you see like something like this for 150 kiloparsec is quite flat, is that, like the stellar populations are kind of the same at all radius, which is telling us that what's happening here, this galaxy with this little neighbor here, are actually merging, and this is a major merger. That's why we don't see any difference in the stellar populations. So it's like a 1 to 1/3 merger. And as we go to the outer parts, we start seeing, like this dip here, which is basically is a signature of this loop here. And when you go to the east, you see here like some bumps that are coincident with all these stellars that we see here. So basically, basically by like having this gradient in color and seeing like more or less like the diameter of the galaxies that are producing these streams, we can guess that what is happening here is that the outer parts of this cluster, of the intracluster of this cluster, are being built by the tidal stripping of Milky Way-like satellites. And I'm gonna go for the part that I'm more interested in, and that is using the intracluster light as a tool to understand the dark matter halo of galaxy clusters. So in simulations, the illustrious TNG simulation, they found that this correlation, which is basically that the slope of the halo, the slope of this intracluster light, correlates with the mass, the total mass of the halo. And as you can see here, we put some of the clusters that we had, and apparently this correlation holds up even to higher masses. But it's not only that, is that it seems that as you go to higher and higher masses, this slope, the slope of the halo, it becomes more and more similar to the slope of the dark matter of the cluster. And that is really, really interesting because it seems that by studying the stars, by studying this intracluster light, we can have a peek of what is going on in the dark matter halo. So here I'm going to introduce you these guys. This is the Hubble frontier fields observations. These are 6 clusters in the redshift range of 0.3 to 0.55, observed in lots of band and very, very deep. These are the deepest observations of galaxy clusters ever done with the Hubble Space Telescope, which means it's a lot. So the Frontier Fields initiative, it was not only producing these really, really pretty images, also because the goal of these observations was to study the high redshift universe. So and to study the high redshift universe, you actually need to understand the clusters itself. So basically, we're using these clusters as gravitational lenses. And because the gravitational lensing produces like distortions and magnification that you need to correct in order to understand what is going on at higher redshift. So this initiative provided around 10 mass models per cluster. And it was because these observations are really, really deep. It's there are some of the best mass models that you can get, basically. And because we were interested in knowing what is, if the intercluster light, if you study the intercluster light can tell us about the mass of the clusters, what we did is basically a comparison of this light, of the mass, and also we throw there also the X-rays just in case. So as you can see, just by looking at it, that the intracluster light, and we are here we are exploring between 50 to 140 kiloparsecs from the inner parts of the cluster, you see that kind of traces very well, like what is going on with the distribution of mass of the clusters. But the X-rays are not doing such a good job. In this case, probably a little bit better, but here just they are way off. And why is that? Because these clusters are or have merged recently or are in the process of merging. So you are expecting the X-rays to just do their own thing, while the dark matter and the stars are more or less in the same location. But of course, we really like to quantify things. Like, if they look similar, it doesn't mean anything. You need to quantify. This is why we use something that is called the modified Hausdorff distance, which basically it tells us about the similarity between 2 shapes. And in this case, well, we used this distance, this similarity. We are quantifying it in kiloparsecs. So in the plot, we have this modified Hausdorff distance as a function of the distance to the center of the cluster. In red, you have basically the comparison between the intracluster light and the mass maps, which is basically the error bars. And because, of course, we don't have the ground truth of that. We only have the mass models And the mass models, they use different things, different priors and different techniques to derive these mass models. So basically to have a control of what is more or less real, we have these rectangles here that are telling us, well, basically it's the comparison between the different mass models. So it's basically like an uncertainty of some sort. And we can say here that yes, it's actually, like as you go farther and farther, you see that still, it holds true, and the intracluster light is a good tracer of the distribution of mass in galaxy clusters. So you're gonna tell me why, and you already know the truth because I told you before. So we know that satellites in massive halos tend to deposit the stars, like at large radius. So basically, you are building something that is extended. This is like the scale is hundreds of kiloparsecs, which is more or less the scale of the dark matter. And that also these stars are not bound to any galaxy, but they are following the potential of the cluster, and the potential of the cluster is the dark matter. So basically, having something extended and that follows the potential of the cluster, if you have two things together, it tells us that yes, it's something that we expected, that the intracluster light is a good tracer of the dark matter distribution in clusters of galaxies. And this is really interesting because when you know how dark matter distributes in galaxy clusters, basically how dark matter distributes in clusters of galaxies, it tells you a lot about basically what is dark matter. So here there are simulations of different flavors of dark matter. So you have our good friend called dark matter, warm dark matter, and two types of self-interacting dark matter. You see that what they produce is a really very different distribution of dark matter in the cluster. So and that is like something that we still need to explore, is if we can use this ICL, which, to be honest, is a little bit easier to get than having, like these gravitational lensing maps. Maybe we can have like enough numbers to actually know what is going on in clusters of galaxies. And I don't know, like, do I have time? Well, so, and it's not only, like the distribution of dark matter, but also knowing where your cluster ends. Because in cosmology, it's kind of important to know where your cluster ends, because, you need to know how to compute the mass of the cluster. So so you have different definitions of this radius of a cluster, and one of them is the splashback radius. And this is kind of neat because it's a physical definition of this radius. So basically, the definition of the splashback radius is when you have your satellite or your object that falls into the cluster, and when it falls and turns around, it not only creates kind of like this boundary, because the material piles up around this. So it not only creates this sort of difference between what is bound to the cluster and what is not bound to the cluster. And you have like this discontinuity in the density profile of the cluster. So in simulations, already they predicted that you can see that if basically you're studying the stars, if you're studying the intracluster light. You see here that this is like basically a radial gradient of the density of the dark matter, which is in black, and of the stars that are in red. You can see here that this is basically where this splashback radius falls, because you have this kind of discontinuity in the profiles. But as you know, like one thing is the simulations and one thing is the observations. problem is that we are talking about, like megaparsecs. So it's you have to go really, really far from the center of the cluster, which presents a lot of problems. And one of them is just, like actually having a profile that is, goes farther enough. But Anthony Gonzalez did this very nice observations with the Hubble Space Telescope, like really, really smart, because it's basically you are doing with your observations like a radial profile. You're just exploring one sideline of the cluster instead of having to map everything. So he created this sort of mosaic of observations. So, like you have like you can actually create build a good mosaic. So you have like this overlap between observations. In one side of this cluster, which is MAX 1149, was one of the frontier fields clusters. And he derived these radial profiles. And as you can see here, so the radial profiles reaches like around 2.6, if I remember correctly, 2.6 megaparsecs. So as you can see, like you have your radial profile, and you have like a drop at around like 1.3, 1.4 megaparsecs. This drop that actually when you build this gradient, you see this is like what we call the caustic that falls and basically is telling you that there's a signature here that may or may not be the splashback radius. So for comparison, there are other clusters from simulations that also present this caustic, but in this case, the signature's a little bit closer to the radius is lower, which might be because this cluster is like a merger of different subclusters, and that might also affect the position of this radius. Sorry, I moved the profiles, but I didn't remove the slides. So okay. So I hope that I convinced you that studying the intracluster light is very important, but again, we need deeper observations, and I think that this shows very well what we are aiming for, right? We have the Sloan, and like it's a really nice image, blah blah blah, but then we are missing a lot of information if we only have the Sloan, because you would think that this is like maybe a star, but no, actually it's a galaxy that is actually interacting with all these galaxies that you have here. And of course, you are missing the really pretty jellyfish galaxy. So what we are aiming for is to have observations that are deeper enough that we can see the intracluster light, but also have enough number of clusters where we can have these deep observations, and that we can actually study the intracluster light, because we need numbers and we need to see all these correlations with redshift, with mass, with the dynamical state of the cluster, and see actually what is going on. Because what we have now is a very rough definition, a very rough understanding of what is going on. So that's where we have here these four facilities. Some that are observing, some that are almost observing, and well, Roman is getting there. These facilities and the combination between them are really important to get understanding of the loss of brightness universe, of the stellar halos, of the intracluster light, and we are really, really excited to have them and to be able to actually explore this loss of brightness universe with in depth, let's say. So these are my conclusions. And I repeat myself again. I hope that I show you that the intracluster light is a really neat tool in order to study how the clusters assemble, to study of course, the most massive galaxies in the universe, these brightest cluster galaxy or BCGs, And that's actually, we can use it to trace the distribution of dark matter in clusters of galaxies and identify the splashback radius, maybe. And I don't know, maybe some other things that we still don't know. And that's why we need deep observations. And please give me money. And well, thank you very much.
Thanks, Mireia, for the nice presentation. I guess we can open a round of questions. I don't know if Alba, so typically, I don't know, we start with the remote or the local. I'm not really sure, but maybe you have questions, just go ahead.
Everything is clear.
Thanks.
Go ahead.
Thanks a lot. Very nice review. I'm really not in the field, so my question might be very basic. So my question is, I know that there are a lot of studies in the X-rays of the intercluster intergalactic medium, and many instruments planned in the future to actually try to take spectra and X-rays of this. So my question is, how can this complement the X-ray band, which you can derive from the optical?
So I didn't include it here, but there's a study of this cluster, MAX 0723, that actually, like it's for creating the mass model of this cluster. But because and that is something that they put a component that actually there was no other indication but the intracluster light that they put like a component around here because of this loop. And there was like not the dynamics, and I don't think that the X-rays were showing that there should be anything there, but they put the component, and the accuracy of the mass maps actually decreased a lot just by adding like a kind of random component there. But like it was like there was a reason to put this component. So I think that maybe maybe this like more study of the intracluster light, and we are still not there just to use that only. But I think that we can use that in combination with the mass maps. And now what the community are trying to include dynamics of galaxies, X-rays, and all this information in basically in all the wavelengths in order to construct mass maps that are more accurate. And I think that this is the most straightforward connection between this and the X-rays.
No questions, Aldo?
So you showed the ratio of the mass as a function of redshift. There was a green square.
Which one? I have too many plots.
The one with the
with
whatever.
this one?
No,
It's a previous one.
This one. Okay, yeah. With the
So you mentioned the points are
observations.
data. Yeah. So this I don't understand. So the y-axis is the ratio of the mass.
Yeah, it's the mass
compared to redshift 0. So
yes.
How do we know?
So because
what will be the mass of redshift 0? This is the factor.
So for what I understand is what they do is, like you observe the BCG, and you observe the galaxies that are around the BCG, and you assume that at a certain radius, these galaxies are going to end up in the BCG. And that probably explains a lot about, the uncertainty, because it might be depending on what amount of mass goes into the BCG. I'm not sure about the exact details of all these studies, but yeah, I think that's
And how could I relate it then to the amount of mass that would be the intercluster?
So the simulations that actually agree a little bit more with the observations they they range a little bit, but it's around 50 to 80% of the mass that instead to the BCG goes to this intracluster light. So basically, it's not this mass that doesn't count in the BCG. Yeah, I mean, this thing is that it's kind of, that part is kind of difficult because even like at redshift 0, that depends a lot on how deep your observations are. So imagine that, you know, you're at redshift 0 and you want to know like the masses that is in your BCG. You have all this intracluster light that's in there, and you also don't know how to. So normally people have a cut between 30 to 50 kiloparsecs to, you know, like this is kind of what we count as BCG, and then you have the stellar halo and you have the intracluster light. It's a little bit complicated. Yeah.
Any more questions?
A few slides later, you have the profiles of the color
Yes.
as a function of rays.
Yeah. This one.
Here.
Yeah.
So I understand. So this becomes lower the further you are, the further away you are.
Yes.
from the input.
Yeah, yes.
So how can I understand this? So why
So-
is the different type of stellar population?
Yeah. So in the center you have the BCG, and they are normally, you know, like red. They are metal rich. They are in general, they are all. I mean, you have BCGs that have star formation, but in general, they are elliptical galaxies, what they call red and dead. And as you go farther and farther, you have like the contribution of, or the less massive galaxies that are building your profile, right? That they're so. And as you can see here, that there's a lot of, I mean, you know, like you have a lot of error. There are ones that are a little bit flatter, and ones that, and that it depends on how the properties of the cluster, right? Because we have in the SMAC 0723 that the profile is really flat until 150 kiloparsecs, basically here. And then, you know, like you have your contribution of like less massive galaxies. So basically, and that is, I mean, that is not only observations. It's always like, you know, like you have like a contribution of what the simulations are telling you. And in the simulations, they see that this is, you know, for example, that would be like a case of, you know, like you are comparing with simulations, and you see that more or less, you know, like what you, this gradient is incompatible with, you know, like having less massive galaxies contribute to your ICL. But in my case, we because we have multi-wavelength observations of the frontier field clusters, we can derive these H and metallicity profiles, and this is where you can see that the metallicity that's in these outer parts is basically consistent with the outer parts of Milky Way like galaxies, because those are these galaxies. That's where the outer parts are going to get disrupted more easily, and that's why they end up. And because you need 4 or 5 of these galaxies to already, you know, like contribute a lot to your intracluster light, is why you get that the metallicity of most of the galaxies, it's around this outer, you know, this range of metallicities.
Thank you for the great talk. I have actually a question regarding another point about SDSS, because here we see that we may have young populations.
You mean in the simulations? No, that was before.
In simulations.
This part. Well, I mean, like I have to. There's a.
Yeah.
Because in this simulation they predict that 30% of the intracluster light is going to be young stars, you know, formed in situ, which I think that is a lot. Yeah.
Is it TNG?
No, those are I don't know which ones, but no. I think that TNG is just
I think
normal tidal stream.
cannot form this.
Okay.
Given the mass resolution. Right?
Yeah, probably. Yeah.
10 to the 5 best. But
Yeah.
So these stars are bluer because they're coming from these galaxies. However, I would expect that they should be all they're not starting to see or traveling distances. There's no starting. But X-ray observations can actually help you with that because you can't go into population, you don't have a brilliant X-ray source, right? So I guess this fragmentation of the expectations. I don't know what are the luminosities of these X-rays. Maybe it's completely off because the focus is coming only to the dust. But I believe that the fragmented picture of the X-rays can give you some information about in situ contamination because these are going to be distinct X-ray sources coming from young populations instead of just hidden gas or something else. But my question is, these simulations, I guess, they're not modeling, right? They cannot model stars that are hypervelocity stars, and that they are also mentioned in situ.
Yeah, with simulations, you always have like this trade-off between the resolution and because I mean, if you want a cluster of galaxy and you are relying on, for example, cosmological simulations, you're not gonna get a resolution that is more than a dwarf galaxy, right? There are some of these that are semi-analytical, but then you have a prescription of what is doing that, right? And so you have to be like a little bit, and I cannot remember the details of this one in particular, but because it's been a long time. But yeah, I mean, like they say 30%, which I think that is a lot, and I haven't seen any other simulation that actually can reproduce any of it. So it's always like, yeah, maybe, but still we are also limited by the resolution that we have in the observations, because I remind you that what we are doing is basically this, that you have a radial profile. So what we have is it's basically a picture of what contributes the most of it. But maybe, like if I'm not sure if X-rays can get there, but it will be like really helpful if we can have something, like extra added information that can point us to, like, oh, there's something going on there. Alvaro, you wanted to say something? No?
Yeah, I wanted some questions. I had some questions, but from an outsider. So is this intercluster light connected somehow to the more diffuse gas that you can observe in the galaxies when you're going far away with hydrogen? Or is this going much farther away than the diffuse gas?
Yeah, I mean, like the scales of the intracluster light are on like, I mean, I would say hundreds, but that depends. Well, it just have like the limits on what we can actually observe. So, like, for example, in the frontier field clusters, the limitation, which is kind of sad, but the limitation was actually the size of the camera. So we cannot reach more than 200 something kiloparsecs because, I mean, you have the edge of your camera. So, but yeah, it's normally in the order of hundreds of kiloparsecs. But I think that the gas is way, and this is basically this is the intercluster light is stars, and it comes from like the interaction between the galaxies and the cluster. So kind of more centrally concentrated than.
And then a curiosity, so connected to the James Webb Space Limited Vision. So you showed this original and then the work that you did. So is this a problem in the processing pipeline that is still there, or has it been fixed?
That I know of, no. It hasn't been fixed. But I mean, thing is that, like the gradient is, because here I just like put it, a lot of contrast, and so you can see it, right? But normally, like if you do basically anything else than what I do, you don't care about this gradient. So, like it's kind of low priority. Normally it's low priority in the list. And that's, I know because of the HST, right? There are like things there in the normal things in the detector. Also, well, the HST is degrading. So the detectors are surviving, let's say. But yeah, because you have to prioritize the things that are gonna be more used, right? That is gonna be of service to most of the users. So yeah, I'm not sure, but I think that's still
because this approach that you follow to fix it is something that could be implemented to other.
Yeah, but personally, I would like, because what we did here is because we downloaded, and that's why it took forever, downloaded the calibrated images, and we basically fit a plane, because we saw that in all the images the gradient just in the same position. We fitted a plane, we correct from the plane, and we stack to get the final image. In my personal opinion, I would like to have something right from the beginning. Also because that we can implement things about the flat fields, the whatever, or other stuff that the instrument, it could be better especially for us, and it's very niche. Data reduction for loss of brightness, it's always like few people that are there, and yeah, the good thing is that we made pretty images. So
thank you.
And I think that is something in the chat.
Okay, let's see. No, it's just thinking. So any more questions from the audience here and remotely? Is there anybody the question for Mireia? Well, if not, let's just thank her again for the nice talk. Okay. Una pregunta.